Flood routing is the process of calculating a flood, either for design, forecasting, or hindcasting purposes. Flood routing can be applied to kinematic, diffusion, and mixed dynamic waves. Routing with kinematic and diffusion waves is described here. Kinematic waves are governed by the equation of water continuity and a simplified equation of motion that considers only gravitational and frictional forces. The equation of water continuity is in which u is the mean velocity and h is the flow depth. In terms of discharge and flow area, the equation of water continuity is for kinematic waves, the equation of motion is in which S sub f is the friction slope and S sub o is the bottom slope. This equation can be expressed as a steady equilibrium rating. Taking the derivative, in which C is the kinematic wave celerity or Seddon celerity. Multiplying the kinematic wave celerity with the water continuity equation and applying the chain rule leads to the kinematic wave equation. Note that the kinematic wave equation is of first order. Therefore, it can describe convection, but it cannot describe diffusion. This fact has significant implications for flood routing. The numerical solution of the kinematic wave equation on a grid system is a function of the Courant number. In which delta x is the space interval and delta t is the time interval. There are many numerical schemes to solve the kinematic wave equation. In practice, the forward in time, backward in space, and forward in space, backward in time schemes remain the most common. A combination of these two schemes is used in the Army Corps of Engineers HEC-HMS hydrologic model. Unfortunately, depending on the prevailing Courant number, these schemes introduce a certain amount of numerical diffusion and dispersion. Numerical diffusion and dispersion arise in a numerical computation due to the finite size of the grid. Numerical diffusion is a first-order error. Numerical dispersion is a second-order error. For kinematic wave schemes, the numerical diffusion is arbitrary and not related to the physical diffusion, if any, of the actual wave propagation problem. Therefore, a numerical solution of the kinematic wave equation remains essentially a conceptual model, not necessarily related to the actual physics of the phenomena. Diffusion waves are governed by the equation of water continuity and a simplified equation of motion that considers only gravitational, frictional, and pressure gradient forces. For diffusion waves, the equation of motion is in the diffusion wave model, the pressure gradient term is responsible for the diffusion effect. The combination of water continuity equation and equation of motion of diffusion waves leads to the diffusion wave equation. In which nu sub h is the hydraulic diffusivity or Hayami diffusivity. Q sub O is the reference unit with discharge. Note that the diffusion wave equation is of second order. Therefore, it can describe physical diffusion, unlike the kinematic wave equation, which cannot. We conclude that the kinematic wave can describe diffusion only by the introduction of numerical diffusion, while the diffusion wave can describe diffusion on its own without the need to rely on numerical diffusion. In practice, the diffusion wave equation is solved numerically using the Muskingum-Cunge method. This method parallels the classical Muskingum method of flood routing. However, unlike the Muskingum method, where the parameters are determined by calibration using measured data, in the Muskingum-Cunge method, the parameters are estimated based on physical and numerical principles. The differential equation of storage is in the Muskingum method, the relation between inflow, outflow, and storage is in which K and X are the Muskingum routing parameters. The parameter K is a time of storage, and X is a dimensionless weighting factor. The substitution of the Muskingum relation into the differential equation of storage leads to the routing equation. With the routing coefficients. The parameters K and X are obtained by calibration using measured data, that is, with stream gauging. Therefore, the method is strictly applicable to gauged streams. The Muskingum-Cunge method is an application of the concept of diffusion wave. The method parallels the Muskingum method, but with the significant difference that the routing parameters are determined on a physical and numerical basis. The physical characteristics are measurable hydraulic and cross-sectional properties. Therefore, there is no need for stream gauging data, and the method can be used in ungauged streams. In the Muskingum-Cunge method, the routing parameter K is the routing parameter X is defining the cell Reynolds number D. The routing coefficients reduced to thus, given space and time intervals, unit with discharge, kinematic wave celerity, and bottom slope, the courant and cell Reynolds numbers can be calculated. Then, the routing coefficients of the Muskingum-Cunge method can be calculated, and the flood routing proceeds with the routing equation. The Muskingum-Cunge method works by matching physical diffusion with numerical diffusion. The method works best for courant numbers close to 1, for which the numerical dispersion is minimized. Assume an inflow hydrograph with peak flow 1000 cubic meters per second, base flow 0 cubic meters per second, bottom slope 0.000868, peak flow area 400 square meters, peak flow top width 100 meters, rating exponent beta 1.6, reach length 14,400 meters, and time interval 1 hour. The time to peak is 5 hours and the time base is 10 hours. The mean velocity is the wave celerity is the unit width discharge is the Courant number is the cell Reynolds number is the routing coefficients are the routing computations are shown in this table. Column 1 shows the time in hours. Column 2 shows the inflow hydrograph. Columns 3 to 5 show the weighted flows. Column 6 shows the outflow hydrograph. Note that the peak inflow is 1000 cubic meters per second at time 5 hours, while the peak outflow is 963.6 cubic meters per second at time 6 hours. The flood peak has attenuated about 3% and the time base has increased to 13 hours.